Section 1. Light. In this chapter we begin with the question, what is light? And we touch on the types of light. We then go about measuring light intensity and work out how cameras can be adjusted to suit different lighting situations. We then look at the scope of light that humans and cameras can see and evaluate the difference between film and digital photos. And finally, we look at colour and how it affects our cameras. I'm not sure that it's necessary to include this diagram, but it's interesting to see the context of visible light. The electromagnetic spectrum is comprised of all frequencies of electromagnetic radiation that propagate energy and travel through space in the form of waves. At the bottom of the spectrum we have radio waves, which are very long and have a low energy. At the top we have gamma radiation, which is minute waves of very high energy. Light visible to the human eye has a wavelength between 380 and 750 nanometers. It sits between infrared and ultraviolet, hence the colours of the rainbow starting at red and ending in violet. Physicists consider light to be both a wave and a particle, which is known as a photon. Without light, you cannot make a photograph. Incidence light is the light that falls on a subject, for example, sunlight or flashlight. Reflected light is light that reflects off a subject. If you illuminate a black and a white object with the same light, they reflect different amounts of light. The black object absorbs more light than the white object. Digital cameras have reflected light meters. These are designed to read the light reflecting off whatever you're pointing the camera at. Problems occur when you photograph extreme contrast or where the instant light enters the camera. Photographers use the exposure value scale to quantify the amount of light. The scale runs from -7 to 23, where -7 is incredibly dim, for example a deep star or the Milky Way, and 23 would be looking directly at the sun with a telephoto lens. In this chart I've shown the more realistic values. In reality, humans can see light from EV-4 to EV16. Anything beyond that requires eye protection. Each step up on the scale is a doubling of the amount of light. So EV1 is double the light of EV0 and so on. Moving one step on the EV scale is also known as one stop. Traditionally, photographers would use a handheld light meter to measure the EV, but they're now built into cameras. You can even get a light meter app for your phone. The photograph shown here was taken at an exposure value of -6. Now that we know what exposure value is and we can measure it, we need to put it into context with our cameras. I'll explain exactly what shutter speed, aperture and ISO are later in the course, but to be getting on with, here are a few quick descriptions. Shutter speed is the amount of time light is allowed to fall on the sensor. It is measured in seconds and fractions of a second. On your camera dial, 1/60th of a second is just written as 60. Each step of the dial on your camera is roughly half the previous value. Aperture refers to the size of the hole in your lens. It works much like the way the iris controls the pupil size in your eye. Aperture controls the amount of light entering the camera. A small hole or aperture has a high f number and a big hole has a low f number. Each step shown on the diagram is a halving of the area of the aperture. ISO is a bit like a volume button. If we turn the ISO up, we brighten the picture. ISO is generally shown as multiples of 2, so we get values of 100, 200, 400, 800, etc. The definition of EV0 is the light required to get a properly exposed photo with an aperture of 1, a shutter speed of 1 second, and an ISO of 100. You can see that if we double the amount of light, for example, if we go from EV0 to EV1, we are moving one stop. I need half the shutter speed to get a proper exposure, which equals one stop, which equals 1 second down to half a second. Equally, I could instead halve the area of the aperture, which is moving one stop, which equals f1 to f1.4. Alternatively, I would need to turn the ISO down by one stop, which equals ISO 100 to ISO 50. If I want to go in the other direction, then I have to multiply one of the variables by a factor of 2. More on this later, but the message I want to get across is twofold. 1. There are many ways we can properly expose a picture from the same amount of light. And 2. Each step in either aperture, shutter speed or ISO is called a stop. We've all taken photos where the sky is burnt out or the shadows are totally black, or both. And there's nothing we can do in software to solve the problem. Dynamic range is the measurement in stops of the difference between solid black and solid white. From an earlier slide, we note that humans can see from EV-4 to EV16. That's a 20 stop difference. Each stop is 2 times the intensity of light to the previous level. So a 20 stop difference is a total intensity range of around 1,000,000 times. The top picture shows a high contrast image that was captured by my camera. The bottom is the scene that I saw with my eyes. This difference is because cameras don't have the dynamic range that humans have. The top-end camera has a dynamic range of around 12.3 stops. That equals a range of about 5,000. Most mobile phones have a dynamic range of around 7 stops, which is equivalent to 128. As a rule of thumb, cameras with more dynamic range tend to be more expensive. Here is a series of 2 pictures taken with a film and a digital camera. The top pair of images are extremely overexposed. Here we can see the film has outperformed digital. There's detail in the highlights. The digital photo, on the other hand, is blown. The bottom pair of images are extremely underexposed. Here the digital shot outperforms the film, which is useless. Although the digital shot is much better, the blacks look a bit grainy. As we now mostly shoot digital, the lesson here is, be very careful not to blow the highlights when setting your exposure. The human eye can see 10 to 12 million colours. Cameras record 3 colours: red, green and blue. Shades of these colours are merged to get the colour that is saved as a pixel. Most computer screens and JPEG photos are what's known as 8-bit. That's 2 to the power of 8 or 256 shades of red, green or blue. This is known as bit depth. When shades of these three colours are merged, we get 16.7 million possible colours. Where black is no colour, 0, 0, 0, and white is 100% red, 100% green and 100% blue. Cameras usually have a bit depth of 14 bits. This is around 16,000 shades per channel or 4.4 trillion colours. So why do we shoot in RAW? Well, we get better colour accuracy, which we'll explain later, and more adjustability in software. White balance is a camera's way of eliminating a colour cast caused by certain types of light. For example, in artificial light there tends to be a yellow cast to our photos. And in the hours after sunset there's a blue cast, as seen in the shot on the left. The standard setting on a camera is automatic white balance, where the camera makes a good guess of the colour temperature and subtracts the cast. But it doesn't always get it right. If you want to be more accurate, you can set the white balance in camera to the lighting conditions, i.e. daylight, cloudy, tungsten, etc. The beauty of doing this is you know the right colour has been applied. It's particularly important to have a constant white balance if you're taking several shots. For example, if you're taking a panorama where you don't want the white balance to move between shots. Some professional photographers go one step further. Instead of choosing a white balance in camera, they take a photo of a black, white and grey card. When they come to edit their photos, they adjust the colours in their colour card photograph and then apply the same settings to their images. You can get a grey card on your mobile phone. As a RAW file has much greater colour depth, there are more colours to play with. A JPEG file has already had its number of colours reduced, so if you play with the JPEG file, the colours are less adjustable. Some manufacturers' files tend to have a bit of a colour cast to them. In my experience, Canon files tend to be a bit yellow and Fuji tends to be a bit magenta.